Hi, hi, it's Professor Jones again. Let's take a look at um, exercises 2.2.8 and 2.2.14. So on exercise 8, we're looking at the graph of a function f, and we want to find the intervals on which the function is increasing, if there are any. So the function is increasing when, as we move from left to right. So if you're moving from left to right, if you're at a point on the graph and you're moving from left to right, you have to go up to get back on the graph when the function is increasing. So if I'm at a point on the graph and I move directly right, away from the graph, I have to go up to get back to the graph if the function is indeed increasing. So if I'm at an interval of increase, at a point on the graph and I move directly to the right, I'm going to have to move up to get back on the graph if I am in an interval of increase. So we notice that when x is 0, that's when the interval of increase begins. This arrow indicates that the graph indefinitely continues to increase. Intervals of increase and decrease are always open intervals. That means that endpoints are never included. So when an interval is open, we don't include the endpoint. And this is true whether I'm talking about an interval of increase, whether I'm talking about an interval of decrease, or whether I'm talking about an interval where the function is constant. The interval is always an open interval, which means endpoints are not included. Okay, and an open interval does not include its endpoints. So we notice that, as we mentioned, this interval starts increasing when x is 0. So that 0 then would be the endpoint of the interval, and that's not included. The function's graph increases indefinitely as I move from left to right, starting at 0. So an indefinite increase to the right, to indicate that in interval notation, I use the positive infinity symbol. We're now asked to find the intervals on which the function is decreasing, if there are any, and we see that there are none. There are no intervals of decrease. If a function is decreasing as we move from left to right, if we're at a point on the function and we move to the right, we'll have to go down to return to the function. So in an interval of decrease, at a point on the function in an interval of decrease, if you move directly to the right, you'll have to go down to return to the graph of the function. And we see there aren't any places on this function's graph where that happens. There's no downhill areas as we move from left to right. Now in part C, we want to find the intervals in which the function is constant, if there are any. So when a function is constant, it will resemble a horizontal line in any interval where the function is constant. So we see that as we come in indefinitely from the left, when x is smaller than 0, we see that the function is a horizontal line, which means the function is constant. So indefinitely from the left is represented with negative infinity, and this continues until 0. Since we're writing open intervals, we don't include this endpoint of 0. We always use parentheses to enclose negative infinity or positive infinity. We always use parentheses to enclose an endpoint when it's not included. Intervals of increase, decrease, and constancy are always open intervals, which means our enclosures will always be parentheses. So let's take a look at exercise 14 in section 2.2. Again, we have the graph of a function, and we want to find the numbers, if any, at which the function has a relative maximum. So that'll be a mountaintop if there is a relative maximum. And so notice we have such a mountaintop here where x is 0. So the number at which f has a relative maximum is x equal to 0. Then we're asked, what are these relative maxima? So maxima is the plural of the singular word maximum. And so the relative maximum are actually the function's value at the point where the relative maximum occurs. So in this example, that would be f of 0. So relative maximum or maxima are always the y values or the function values. And in this case, we see that that's y equal to 2. So this is something that's always a little confusing for people. The relative maximum occurs at x equal to 0. The relative maximum is 2. So the x value is the value at which the extreme value, in this case a relative maximum, occurs. The y value is the actual value of the relative maximum. Now we're being asked in part B to find the numbers, if any, at which f has a relative minimum. And so this will be a valley or lowest point. So notice at x equal to negative 3 and x equal to 3, we have a valley or a lowest point in that particular region of the function. We notice that the y value corresponding to negative 3 is the same as the y value corresponding to positive 3. So the function's value at negative 3 equals the function's value at 3. That's the y value of negative 1. So in this particular case, this is interesting. There is a single relative minimum. It occurs, though, at 2 different values. So the relative minimum occurs at x equal to negative 3 and x equal to 3. The relative minimum is the y value of negative 1. Also, I want to point out that in this particular case, the relative minimum is also the absolute minimum. The relative minimum of y equal negative 1 is actually the lowest point on the graph. All other points on the graph lie above this. The relative maximum of 2 is not an absolute maximum, though, because these arrows on the ends of the graph indicate an indefinite increase of the function. So eventually, if we extend the function far enough, we'll have values that lie above y equal 2. So 2 is a relative maximum, but it's not an absolute maximum. Negative 1 is a relative minimum, and it's also an absolute minimum.